Good afternoon, everyone. My name is Aldrich, and welcome back to my two series podcast about the innovation and discovery of pi. So, if you haven't known yet, I've made one podcast before about Archimedes' discovery in the world of pi. So, if you haven't listened to it yet, make sure to check it out because that podcast and this one interconnects. Although, if you haven't, don't worry because the topic of this video is rather different from that one. So today, I'm going to continue my discussion about the discovery of the world of pi. This time, I'm going to talk about Newton's inventions and how his ingenious and creative mind revolutionized pi forever. So, if you haven't watched that podcast that I made last time, basically, Archimedes found a method to calculate pi using geometry. He created a shape with a large amount of sides, and the perimeter of it will be near to that of a circle. So, he could approximate pi that way. However, this method is long and tedious, and it could take weeks to even approximate pi to just several decimal digits. So let us enter Isaac Newton. It was at the year 1666, and Newton was inside his house, being quarantined due to the spreading of Black Plague at the time. At that time, he was just playing around with simple expressions and equations, like 1 plus x squared, that's equal to 1 plus 2x plus x squared, 1 plus x to the third, that's 1 plus 3x plus 3x squared plus x to the third, so on and so forth. However, Newton found about a simple pattern that can allow him to calculate the binomials easily. He found out that if we look at the coefficients of the expressions, for example, 1 plus x squared, the coefficient of it is equal to 1, 2, 1. 1 plus x to the third, the coefficient is 1, 3, 3, 1, so on and so forth. Turns out, these coefficients are actually the numbers in a Pascal triangle. 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, so on and so forth. So, we can find the coefficients of a binomial using the Pascal triangle, because the exponent of a binomial is actually the row of the Pascal triangle. For example, 1 plus x squared, the exponent is 2, so it corresponds to the second row of the Pascal's triangle, being 1, 2, 1. But how do we find out a certain row of Pascal's triangle easily without constructing the whole triangle? Well, luckily, Sir Isaac Newton have found a binomial theorem. It goes like this. 1 plus x to the nth power is equal to 1 plus n times x plus n times n minus 1 times x squared over 2 factorial plus n times n minus 1 times n minus 2 times x to the third over 3 factorial, so on and so forth. However, don't get intimidated by the long and winding equation for the binomial theorem, because turns out it's pretty simple. But I'm not going to discuss much about it. I'm going to discuss about what Newton did with it. So, basically, at that time, there was a general rule that the binomial theorem can only be used when n, the exponent of the binomial, is only a positive integer. However, is this really true? That is what Isaac Newton sought to find out. Basically, what he's trying to do is to find out new rules that can be applied for the formula. So, Newton tried n equals negative 1, which theoretically should not apply to the formula. However, Newton insisted on doing it, inputting n equals negative 1. So, we get that 1 plus x to the negative 1 is basically just 1 over 1 plus x. So, what happens to the binomial theorem? Well, we would get that the terms alternate back and forth, making 1 over 1 plus x equals 1 minus x plus x squared minus x cubed plus x fourth, so on and so forth. However, Newton tried to prove this formula by multiplying both sides by 1 plus x, so it should be equal to 1 this time. And, surprisingly, it is equal to 1. When he derived the formula, all of the terms will cancel out, leaving only the term 1. All of the mathematics in here, if you want to try out, but the equation is certainly correct. So at that point, Newton had proven that the binomial theorem can be used when n is a negative integer. So, I had explained before that the coefficients of the binomial corresponds to the number in a certain row of Pascal triangle. So, if the binomial theorem can include negative number, doesn't that mean we can extend the Pascal triangle using negative numbers? Well, that's exactly what Newton did. he extended the Pascal triangle with negative numbers. So let's look at the first number in the Pascal triangle, the number 1. Before that number, we can add an extra row filled with other numbers we obtained from the binomial theorem. We found that the result has to be 1, because in the binomial theorem, the result was 1. So we can start with 1 and 0, because they add up to 1, which is what we're needing. However, because the terms of the binomial theorem are infinite, we need to keep adding more numbers. However, we still need to keep those total number equal to 1. So we can add 1, negative 1, 1, negative 1, so on and so forth. Because 1 and negative 1 cancel each other, so this is what we need. So we now can extend the Pascal triangle to add even more rows. Before the row 0, 1, negative 1, we can add even more numbers that we can obtain from the binomial theorem, making the Pascal triangle even more deep and much more complicated. However, after proving that the binomial theorem can include negative numbers, he didn't stop there. He, once again, tried to test the binomial theorem to its limit, this time by trying out decimal numbers instead of integers for the binomial theorem. So he tried to plug in that the exponent is equal to half. Firstly, we know that anything to the power of half is equal to the square root of it. So it's equal to square root of 1 plus x. And what he gets, that it will give an infinite series, which is square root of 1 plus x is 1 plus half x minus 1 over 8x squared plus 1 over 16x to the third, and so on and so forth. And what do you know? The equation still remains true. You can work out the numbers and the result is still equal. So, the binomial theorem actually can be used for decimal numbers. However, firstly, let's go back to the Pascal's triangle and try to add even more rows of numbers from this finding. So basically, for the row 0.5, because that's the exponent that we input to the equation, we can add the numbers 1, half, negative 1 over 8, positive 1 over 16, so on and so forth. So we can add even more rows in the Pascal's triangle with decimals and integers. And not only that, we can even add more decimals between it, like between the row 0 and row 0.5, we can add even more sequence of decimals, and so on and so forth. So, after Newton's discovery, not only that the binomial theorem can include integers and negative numbers, but the Pascal's triangle had become more complex, containing decimal integers, containing negative integers, so on and so forth. However, Newton was particularly interested with the number half. This is because if you have an equation of unit circle, which is x squared plus y squared equals 1, we can solve for y, and that would be 1 minus x squared to the power of half. This is basically the expression 1 plus x to the half, but we just replace x with negative x squared. So he ended up with the following equation: 1 minus x squared to the half power is equal to 1 minus half x squared plus 1 over 8 x to the fourth, so on and so forth. Basically, this was just the same equation as before, but the exponent of x is doubled, and they switch signs. Positive become negative, negative become positive. So at this point, what Newton now have is an equation of a circle using the binomial theorem. So, how did Newton calculate pi using this equation? Well, fortunately, he had just invented calculus. So, what he realized is that if he integrate that equation under a curve, using the value from 0 until 1, we would get the area of that curve, which is basically a quarter circle. So now, after integrating the equation, Newton had already found the area of a unit circle, which we can figure out the value for pi. This is because the area of a quarter unit circle would be simply pi over 4. So, what Newton did after this was that he calculated the integration of that equation, and it will be all equal to pi over 4. He simplified the integration of it, and we will get a simple solution of x using simple arithmetic equations. So, what Newton got was that when x is equal to 1, pi is 4 times 1 minus 1 to the half times 1 to the third over 3 minus 1/8 times 1 over 4, so on and so forth. So what Newton now have is an equation that can revolutionize the whole mathematics society. So now it's all done, right? Well, not quite. Newton, in fact, went ahead and added one final tweak into the equation to make it far easier to calculate. Instead of integrating the equation from 0 until 1, he decided to integrate it from 0 to half. Why is this? Well, if Newton integrated from 0 until half, then the equation's size will decrease extremely, decreasing it with a factor of x squared, which will make the equation far easier to calculate. However, what is the area under that curve when we integrate it from 0 until half? Well, we would get an area of pi over 12 plus square root of 3 over 8. So the only thing left to do is to find the integration of the equation, isolate the value for pi, and now we get a far easier equation, which is pi is equal to half minus 1/6 times half to the third minus 1/8 times 1/5 times half to the fifth, so on and so forth. And to prove that this equation is very powerful, let's just try to compare it to Ludwig van Coulen's computation. So, if you have listened to my previous podcast about the bisecting polygons method that Archimedes had developed, a Dutch mathematician, Ludwig van Coulen, spent 25 years to figure out pi to the 35th digits. However, if we use Newton's equation, we only need to count the first 50 terms. That would take mere days, hours even, if you're really great at mathematics. So, just think about it. 25 years of work now can be cut off into only several days using Newton's equation. So what Newton did was not that hard. He just figured out a binomial theorem using decimals, and then used the equation of circle, integrated under a curve, and it's done. Just those three simple steps. And even with only three simple steps, Newton was able to revolutionize the whole mathematics society. And that, everyone, is the story behind how a man found a discovery that revolutionized the very mathematical world. And to think that it all started from him playing around with simple binomials at home. How fascinating. My name is Aldrich, and thank you for listening.